Welcome to This Explainer. Today, we're diving into one of the most mind-boggling concepts in all of science. We're talking about quantum entanglement. Now, I know it sounds like pure science fiction, but it is actually the very real invisible thread that connects the literal fabric of our universe. And the best part? To understand how it works, you don't even need a PhD in physics. Actually, we're going to start with a super simple, everyday trip to a fast food drive-thru.
Picture this. You're on a long drive, you're absolutely starving, and you pull up to the drive-thru window. You order a hot dog and a hamburger. The cashier hands your food over, but they give it to you in two completely identical, perfectly closed boxes. Looking at them sitting there in your passenger seat, you have absolutely no idea which box holds the hot dog and which holds the burger. Right now, they're a total mystery. But the solution here is instant, right? Obviously, the exact second you pop open one box and see a hamburger sitting there, you instantaneously know that the other box contains the hot dog. You didn't even have to crack the second box open to look inside. Because the contents were permanently linked by the order you placed, discovering the state of one instantly revealed the state of the other. So in a very basic, everyday sense, those two boxes are entangled. All right, let's step out of the drive-thru and officially tumble down into Section 1, the quantum rabbit hole. So there is a radical difference between our predictable everyday world, what we call classical physics, and the microscopic quantum world. Sir Isaac Newton's classical physics basically tells us that an apple sitting on a table is going to stay right there until some physical force moves it. Makes sense, right? But when things get incredibly small, all those reliable rules completely break down. In the quantum world, reality becomes so deeply uncertain that our apple could, hypothetically speaking, exist on that table and all the way on Mars at the exact same time. And when we say incredibly small, we really mean it. Quantum mechanics is the language of subatomic particles, your protons, neutrons, photons, and electrons. Just to give you a sense of the scale we're talking about, picture a sewing needle. The sharp, microscopic tip of that needle is actually large enough to act as a seating area for literally billions of electrons. That is the impossibly tiny, mind-bending scale we're dealing with here. Think about it like this. If an alien raccoon from another planet suddenly asked for your identity, you'd probably give your name, your species, and your planet just to specify exactly who you are. Well, scientists do the exact same thing to identify electrons using 4 specific coordinates, which you can see listed right here. Now, no two electrons share the exact same 4 numbers, but for the rest of this explainer, we are going to strictly focus on that last, highlighted one at the bottom, the truly bizarre and fascinating nature of the electron spin quantum number. Which brings us right to Section 2, superposition and dead cats.
Let's see how this all builds together. Because this electron spin is exactly where reality starts to get remarkably weird. It doesn't behave at all like the objects in our normal classical world. An electron can have a positive spin, which we call spin up, or a downward spin, called spin down. But here is the real kicker. Until we actually measure it, the electron isn't doing just one or the other. Think of a spinning coin. While it's spinning really fast on a table, is it heads or tails? It's kind of a blur of both, right? An unmeasured electron acts the same way. It exists as both a positive and negative spin simultaneously. Scientists call this incredible phenomenon a state of superposition.
And this perfectly illustrates the core concept behind one of the most famous thought experiments in all of science, Schrödinger's cat. Devised by Erwin Schrödinger, it basically asks you to imagine a cat placed in a sealed, soundproof box along with a random radioactive hazard. Because the hazard's trigger is entirely random, until you actually physically open the box to look, you have to consider the cat to be in a superposition. It is essentially both alive and dead at the exact same time. The wild part is that the very act of looking is what forces reality to make up its mind. Opening that box, or in quantum terms, measuring that spinning electron, forces it out of its blurred superposition and makes it pick a single, definite state. Physicists call this mind-blowing event the collapse of the wave function. So simply by interacting with the external world, the particle's infinite possibilities instantly collapse into one concrete reality.
Let's keep following this logic into Section 3, spooky action at a distance.
So we know particles can be in 2 states at once, and measuring them absolutely locks them into one. Now let's see what happens when we combine that idea with our fast food drive-thru logic from earlier. This leads us directly to the most far-out phenomenon in all of quantum theory. Just like those fast food boxes, when 2 electrons are generated together or share close spatial proximity, they can become deeply entangled. They completely shed their individual solo states and instead form a single united quantum state. From that moment on, their fates are permanently linked in opposite spin states, meaning if one ends up being spin up, its partner will always immediately become spin down. Here is the absolutely crucial takeaway. Distance completely stops mattering. If we take these two entangled electrons, leave one sitting here in a lab on Earth, and send the other one millions of light years away to the Andromeda galaxy, that invisible link remains perfectly intact. If we measure the Earth electron and find it has an upspin, we instantaneously know without a shadow of a doubt that the electron in Andromeda just collapsed into a downspin. But hold on a second. Let's really think about the massive implications here. If the electron on Earth affects the one out in Andromeda instantaneously, does this imply that information just somehow communicated across the entire universe faster than the speed of light? I mean, that completely breaks the absolute most fundamental laws of physics we have. And guess what? This exact contradiction deeply, deeply bothered Albert Einstein. Back in 1935, he pointed out that entanglement totally defied his famous theory of special relativity. That's the theory that proves, mathematically with E equals mc squared, that absolutely nothing can travel faster than the speed of light. To Einstein, it just seemed completely impossible. And it actually took 3 whole decades before a scientist named John Stuart Bell figured out a real-world method to test it and ultimately prove that entanglement was, in fact, 100% real. The very idea that two particles could interact instantaneously from such a massive distance without ever crossing the physical space between them was so profoundly disturbing to Einstein's understanding of reality that he famously mocked it. He dubbed the entire phenomenon spooky action at a distance. So now that we've traversed this incredibly weird quantum rabbit hole, we can finally define quantum entanglement formally. It is an unbreakable, instantaneous connection between particles. Regardless of the vastness of time and space separating them, they share a single quantum state forever. What happens to one instantly dictates the reality of the other. Let's look at how this applies today in Section 4, Real-World Quantum Magic. Right now, you might be sitting there thinking, okay, this is all abstract math and microscopic theory. Why does it actually matter to me? Well, let's look at how scientists are actively using this spooky science to fundamentally change our everyday world. Entanglement isn't just a theory anymore. It's a practical tool. It's the secret engine powering the next generation of our technology. For instance, in 2007, Switzerland used quantum cryptography to create an ultra-secure, tamper-proof voting system. Because if a hacker tries to intercept entangled photons, their quantum states instantly change, immediately triggering the security alarms. Meanwhile, over in Japan, researchers are using entangled photons to build groundbreaking microscopes capable of gathering massive amounts of previously invisible data. And take a look at this staggering number on screen, 33 billion. Think about that for a second. By linking atoms into a shared entangled state, scientists at the National Institute of Standards and Technology literally created an atomic quantum logic clock so impossibly accurate it wouldn't lose or gain a single second in 33 billion years. That is the kind of breathtaking precision that will completely revolutionize our global GPS systems and the high-speed synchronization of our stock markets. Oh, and yes, quantum teleportation is actually a real functioning scientific process happening right now. But before you go trying to beam yourself to work to beat the morning traffic, remember that we are currently only teleporting complex quantum data, not physical matter. Still, the ability to instantly transfer data across space without it physically traveling the distance in between, that is literally the dawn of the ultimate unhackable quantum internet. Finally, let's gaze ahead in Section 5, the future of quantum. So where does this spooky action actually take us next? As we look up from our laboratories and out into the vast cosmos, what mysteries can entanglement help us solve? Believe it or not, a staggering 95% of our universe is still a total mystery to us. That is exactly why organizations like NASA are heavily investing in this space. They're actively testing entanglement in extreme orbital environments to shed light on the highly elusive nature of dark matter and dark energy. By understanding the invisible quantum threads connecting the universe, we can unlock the fundamental knowledge required to make deep space exploration a viable reality for humanity. Look, if your head is spinning right now in a superposition of awe and total confusion, please do not worry. As the brilliant Nobel laureate Richard Feynman once noted, if you think you understand quantum mechanics, you don't understand quantum mechanics. The sheer impossibility of the quantum realm means that being thoroughly confused is exactly the point. But it leaves us with an absolutely incredible final question to ponder. If our entire reality is built on microscopic particles that can instantly communicate across billions of light years, what other invisible connections are silently shaping the universe around us right now? Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.